Hello and welcome again to my Physics Online video lecture series. In today's video we're going to be discussing Newton's second law, Newton's second force law if you'd prefer. And in my original video in which I introduced all of Newton's force laws, I noted that Newton's second law was certainly formulated in some form or fashion before Newton, specifically by René Descartes. However, Newton took it and maybe formulated it a little bit more clearly and also combined it with the other laws to make a more coherent whole of these force laws. So what does Newton's second law actually say? Well, you're going to get today the introductory version of that. Newton's second law basically relates the amount of force applied to an object to the acceleration that the object will undergo via the object's mass. So you'll recall from a previous video that we discussed the difference between mass and weight, and that we noted that mass was a sort of measurement of the inertia that an object had. So in writing, Newton's second law just says that the sum of forces acting on an object will be equal to the mass of the object times the acceleration of the object. And we should note, of course, that sometimes the sum of forces is also represented as what's called the net force. Sometimes that's capitalized, sometimes that's lowercase, depending upon your textbook, and sometimes it's also represented as the total force. So this might be FTOT or FTOTAL. These are all common ways of representing the same thing. What does it mean? Well, we discussed this a little bit in the video about Newton's first law, that you can have more than one force acting upon an object. And so if, for example, I have a force here, F1, and I have another force here, F2, and I have another force acting here, F3, and maybe I have a final force here, F4, then by definition of what a total force is, the total force, or the sum of forces, is going to be basically just F1 plus F2 plus F3 plus F4. And more forces if there are more forces present, and fewer if there are fewer present. Okay, so this is what it is regardless of Newton's laws. So this is kind of definition. And this definition says add up every force that acts on the object and you'll get some total amount of force. So as a vector sum, this net amount of force might, for example, be like this. So this might be my sum of forces. Alright, so does any one of these forces acting alone produce an acceleration? Well, if it really was acting alone, then yes. But many of these are not actually acting alone, and so we do take the net total. Another thing to note about this is that there's this concept of an unbalanced force. So what is an unbalanced force? Well, an unbalanced force basically means you apply a force to an object and there's no other force to cancel it out. So if this object was just floating in space, for example, and you were able to maybe attach a rope to it and pull the rope, then you'd get some force, F1 or F rope or F tension, whatever, and this force would therefore be unbalanced. So this unbalanced force in this case would be the same as the net force. So this is same as net force, or same as sum of forces acting on the object. So if a problem ever specifies that there is an unbalanced force of so many newtons acting on an object, that basically means that the net force or the total force or the sum of forces is that many newtons. So if we say there's an unbalanced force of 100 newtons, then that means that when you've added all of the forces together acting on the object, you get a total magnitude of 100 newtons. And then maybe there's a direction specified, maybe there's not. So what does Newton's second law kind of tell us? Well, it tells us that if we have more force, then we'll get more acceleration. It also tells us that more mass means it's harder to accelerate. So more mass means harder to accelerate. That means more difficult to change the velocity. Remember that acceleration is a change in velocity. So if more mass means harder to accelerate, then it also means harder to change velocity. And so we can see already that mass must be some form of inertia. If you have an object that's twice as massive, or if you have two objects and one is twice as massive as the other, then you're also going to need twice as much force to give the same acceleration, ergo the same change in velocity for the larger of the two objects. In some sense, we can say that there are three forms of Newton's second law. They're really just the same equation three times. So this more mass means harder to change velocity is akin to saying that the acceleration of the object is the net force divided by the mass. So more mass, bigger number here, smaller number here. On the other hand, more force means more acceleration for the same mass, of course. Conversely, we might say that more mass means more force is needed for the same acceleration, or more mass means less acceleration for the same force. Those are two ways of framing the same thing. The second way, the more mass means more force for the same acceleration. It could be expressed as sum of forces is mass times acceleration, or if you'd prefer, the net force is the mass times the acceleration. And that's just in magnitude form. And that just is Newton's second law in its usual framing. Finally, we might kind of solve for the mass. In other words, you can use the amount of force and the amount of mass to determine, the amount of force and the amount of acceleration to determine the mass. This is again rearranging our acceleration, or our equation from sum of forces is mass times acceleration to say that the mass is the sum of forces, or if you prefer, the net force divided by the acceleration. Okay, so these are all just different things that we're doing with the same Newton's second law. So what is an example of Newton's second law? All right, for example, we might ask how much total force is needed to accelerate an object 30 kilograms, a 30 kilogram crate, by 0.4 meters per second squared. So how much total force? This right here is basically asking for what net force. What is F net? This right here is giving us the mass. This right here is giving us the acceleration. Newton's second law says that this net or total force is the mass times the acceleration. That is 30 kilograms times 0.40 meters per second squared. Okay, and that gives us 12. So we have 12 newtons. Another example. Suppose we have an unbalanced force of 24 newtons. Again, this is another way of saying F net is 24 newtons. It produces an acceleration of 0.8 meters per second squared. This is A. And what we want to know is, what is the object's mass? That's m. So again, we can say F net is equal to m times A. Therefore, m is F net over A. And so that is 24 newtons divided by 0.80 meters per second squared. It follows that the mass of the object must be 30 kilograms. One thing that is very important to note when using Newton's second law is that you need to make sure that the forces are in fact acting on the same object. That statement is also valid for Newton's first law, by the way. Now, sometimes we can get around this by defining a virtual object or defining a system as an object. And along similar lines to defining your virtual object or defining a system as an object, you have to be careful that you're only looking at external force. Basically, this latter stipulation that only externally applied forces count means that if you have, for example, two objects that are tethered together and you want to accelerate the pair of them, then the tension of the tether between the two objects would count as an internal force if you're defining both objects to be part of what we might call object system, but it would be an external force on either object taken on its own. So maybe you have grabbed onto one of the two objects and are pulling it, and that causes both to accelerate, and there is a tension present. You kind of have two ways of going about solving this problem. One is to look at the tension as an external force on object 1 and also an external force on object 2, and do sum of forces on each of those two objects and figure out what the acceleration is, assuming that the two are accelerating together since they are tethered. The other is to treat both objects together as if they are a single virtual object or a single system-like object that are accelerating together, and in this case the tension becomes an internal force. As an example of this idea, let's consider an ideal Atwood's machine. So Atwood's machine basically consists of a pulley, which is sort of fixed in place, and then over the pulley is run a string, and attached to the string are a pair of masses. So usually one of the masses is going to fall or descend, we'll call that one M1, and the other one is going to rise or ascend. And so if we have this pair of masses, they are going to be moving together because of this string. So as this one falls, this one rises. If this one falls by 2 centimeters, this one rises by the same 2 centimeters. What we want to do here is solve for the acceleration of, let's say, object M1. Well, one option for doing that is to get the sum of forces on object M1. So we would have a tension force upward, we would have a gravity force downward. So our sum of forces would say essentially that force of tension minus mg, or m1g, should look like m1a. But now we got to figure out tension. We could go to object 2 and set up a similar equation. The two accelerate together though, so instead of doing that, we can set up our virtual. Our virtual object is kind of like both objects put together, with the total mass being m1 plus m2, and the total forces being an m2g upward and an m1g downward. Our Newton's second law now looks like solving for the acceleration, we get the total mass. So now we plug in the numbers, and this gives us an acceleration of 0.65 meters per second squared. All right, thanks for watching.